All right, so now we're going to talk about Chapter 4, which has analog to digital conversion. So the basics between analog to digital conversion, which is abbreviated ADC sometimes, A2D for analog to digital, A/D, it depends on where you're reading it, was we're taking a variable voltage input and we're converting it to a digital number. So digital is how computers store numbers, so that's the reason we have to do this conversion. And the basics are if you stack these two rulers next to each other in this figure here. So we've got voltage on the left and the digital on the right. We have a 10 volt maximum input and a negative 10 maximum input. So the voltage input range is negative 10 to 10 volts. And that is being mapped to this digital side using a 3-bit, which you'll never see in real life, 3-bit analog to digital converter. So we have a 3-bit number, which can count from 0 to 2 to the 3 minus 1, which is 0 to 7. So all of the voltages in this whole range between negative 10 and 10 are either going to be 0, 1, 2, 3, 4, 5, 6, or 7. So that's the thing with analog to digital is you have a finite number of choices. So a voltage in this range would get mapped either to the 3 or the 2. This would get mapped to the 5. So you can see it just maps straight across. The more bits you have, so that's a major specification of the analog to digital converter, is how many bits it has. It makes a finer scale on this right-hand side. So with n bits, you can count from 0 to 2 to the n minus 1. So a 3-bit goes from 0 to 8 minus 1, 0 to 7. More commonly, you'll find 8-bit analog to digital converters, which go 0 to 255, 10-bit, 12-bit, 16-bit, and more. So the voltage range ends up digitized using this scale. So we have volts coming in. Coming out, we just have a number, and it doesn't really have units, so unitless is really the right way to think about it. But we like to put units on things, so you'll commonly hear them called counts or ticks. So analog to digital counts, or A to D ticks, are commonly said. Please don't call them bits, because bits is used for how many digits we can store, not the units on our voltage. So you'll hear that. I saw that a lot on YouTube, but I don't approve. So don't call them bits. They're counts or they're ticks. So this is a copy and paste of figure 4.7 in our textbook that has the equations for converting. And again, they're just basic mapping. Now we're mapping from a low voltage called VRL and a high voltage called VRU, the range, voltage range upper, voltage range lower, and we're mapping that to the digital side between 0 and 2 to the n minus 1 for our n-bit simple binary analog to digital converter. So simple binary is the ones that you'll see almost all the time, and this is the equation with an input voltage VI and then the range voltages and the number of bits. Int here means you round it off. It has to be a whole number. Some A to Ds round off, some truncate, round down all the time. Usually it doesn't matter. You have enough bits that you don't care really what happens with that last number. If it does, you should probably get a better analog to digital converter. But you can read in the datasheet whether it rounds off or truncates. There are some 2's complement A to D converters, and they use this formula to go from analog to digital. Converting back, you just turn that formula around. You don't have to do the rounding off because it's already been done. We're going back to an analog voltage. So given the digital output, this side from the computer, you want to know what the voltage is. So this is the equation for the simple binary, the usual kind. If you're in 2's complement, it's this equation. So let's do an example using the specifications of the Arduino analog to digital converter, which we're using this semester. It's a 10-bit analog to digital converter. The inputs can range from 0 to 5 volts, and it's a simple binary converter. So if Vin is 3.3 volts, what's the analog to digital converter reading? So you should do that right now. Pause the video and see if you get the right answer. Okay, here's what I got. We put 3.3 in for Vin, VRU, VRU, VRL, and N. So the number is 675.84, and we round that off to 676. So if you actually program an Arduino, this is the number you get out of its analog to digital converter, and you have to convert it to volts yourself. In LabVIEW, they take care of that for you because they know the specifications. The other thing is if this formula gives you a number that's negative or bigger than 2 to the 10 minus 1, it should be saturated at that value. A couple of definitions that go along with analog to digital conversion, resolution and quantization. Resolution is important. It's the smallest change in voltage that you can detect. It's really what happens if you go up by 1 on the digital side. And if you put a 1 in for DO, you'll get this. So it's the upper voltage minus the lower voltage divided by 2 to the n. So for an Arduino, 5 divided by 2 to the 10 gives us 4.88 millivolts. So about 5 millivolts is what you can detect on an Arduino. So if your sensor puts out very small voltages, you won't see any change on the Arduino. And so the solution is always adding more bits. That makes this number smaller. It's the denominator. Quantization is related to resolution. It's the error from round off. And so it's a plus or minus kind of number, plus or minus half the resolution. So you just put this in front of the resolution formula. And what that says is if you added this to any measurement, it won't change the analog to digital converter reading because it's within the round off error. And again, if this is too big, add more bits by a fancier analog to digital converter. Chapter 4 has a lot of information on how analog to digital converter works that we don't really go over in this class because we're not electrical engineers. But here, there are some interesting figures. So this is, and there are many different ways to do analog to digital conversion. This is a ramp analog to digital converter where the input voltage is shown here. This is voltage versus time. And there's a circuit in the analog to digital converter that ramps at a known rate, goes from 0 up to the maximum. And there's a circuit, another circuit that compares this to the ramp, and when they match, it sets a flag, it notifies things. And so you start a stopwatch and you wait until these match, and then knowing the time lets you know the voltage. So that's where the units of ticks comes from, because they're timer ticks, but also counts makes sense. So that's a ramp analog to digital converter. They're slow because it takes a while. You have to wait for this ramp to get up to the actual voltage to work. But they're very simple. This is a different kind of analog to digital converter. It's a parallel analog to digital converter. So we have the input voltage down here coming into a circuit, and we have a big voltage divider set up over here with the reference voltage, the upper voltage. And these are comparators. They're a digital output, either a 1 or a 0, if one input is greater than the other. So they're sort of the backbone of an analog to digital converter. And basically, if your input is greater than this one, you get a 1 here. If it's greater than this one, you get a 1 here. And so you'll get 1s going up the chain until you find the value. And you can convert that to a digital number with this encoder setup. So this is a parallel one. It's fast because it instantly gives you the number, but if you have an 8-bit system, you need 255 of these, so lots of components in the parallel.